So as she introduced us, I'm Christine Harvey. I work for the MITRE Corporation. Alex Gartner, my colleague, is here with me. So we have kind of a two-part talk. So first I'm going to talk about our corporate GPU resources and how we use those at MITRE. So we have traditional HPC clusters that have GPUs on them, and we have those set up for users. And then Alex has worked on some container systems that make it really easy for users to log in, set up a Docker container, and get running right away. So to give a little bit of background about how MITRE works and the setup we have, so MITRE operates federally funded research development centers. So we do all sorts of research from companies, or from organizations ranging from the Department of Defense to Census and IRS. We're an organization of about 8,000 people. So it's a pretty diverse set of skill sets, tools. We have all sorts of engineers, researchers. The people I work with mostly specialize in fast prototyping and quick development. So they propose research projects either to our sponsors or for our internal research program. They want to get started, get spun up on GPUs right away, and have results quickly. So I don't know if people here are more familiar with the GPU side, the container side, or the HPC side, so I'm going to kind of walk through the HPC systems we have and how we manage those at MITRE. But we have two high-performance computing systems, so MITRE split up into tech centers, portfolios, projects, and then we also have corporate operations. So in corporate operations, we manage things like shared computing resources. We have an internal cloud. We have a group that helps people get on AWS. We also manage things like Jira, Atlassian, DevOps, all sorts of things like that as well. So I work on high-performance computing systems. So we have the Senate cluster. I first started doing this job in, I would say, about 3 years ago. And so we bought a cluster. We put it in the McLean campus. We've got head offices in DC and then also one in Boston. So we bought this HPC system. It's a single rack. It's got about 1,000 compute cores. It's got a little bit of GPU power. We really weren't sure how much people wanted to use GPUs at the time. So when we went into this, we kind of, just dipped our toes in buying GPUs for people to use. It's got storage space, and it's also got 56 gigabit per second InfiniBand. And so after we bought this cluster, we knew we wanted to buy a second one for our Boston campus a little bit later. So we sent out a survey to users, and we asked them what's missing. So what did we do well? What's missing from this cluster? And from basically everybody, they all said, we want more GPUs. We want to be able to do GPU computing. This is where all of our work is going, so we need that, and that's what's missing now. So we bought a new cluster from a vendor called MicroWay in FY17. So we bought this about about a year and a half ago. This one has 240 compute cores, so it's a lot smaller on the compute side, but it has 24 GPUs. Currently, it's a mix of P100 and V100s. More storage space. The other thing they mentioned was they needed way more storage, faster interconnect, and then this one also has an FPGA-ready node. And then the other thing that we have, the way we have this set up currently at MITRE is that this is all free for anybody at MITRE. So if you're a MITRE employee and you're doing work for one of our sponsors or for the internal research program, all you have to do is send an email to our ticketing system asking for an account, and we get you set up. There's no restrictions on how much you can use the cluster. As long as there's space, you can use the cluster and run your job. So it's a little bit more flexible compared to using cloud resources because they don't have to, they can be a little bit more risky, right? Like if you log into the cloud and launch a bunch of jobs and they don't do very well, your manager's gonna ask you why you wasted all this money on the cloud. Here, they don't really have to do so much of that. There's a little bit more room to play and experiment around. So if you're not familiar with high-performance computing systems, this is what our Senate cluster architecture looks like. So we've got a head node, which is the brains of the operation. This is where the scheduler runs, where you do your account authentication, all sorts of things like that. We've got login and development nodes. So Senator 01 through 03 are where users SSH, they download their code from GitHub, they set up their Anaconda environment, they make sure everything works properly, and then they'll launch their code to run on the scheduler. And so if you look at this diagram, we've got everything hooked up to the MITRE network. We've got a 10 gigabit Ethernet link. We've got InfiniBand connection, IPMI network, which is how you manage things. And then we've got head nodes, login nodes, compute nodes with that giant purple block at the top. And then below that are all the GPU compute nodes. So we've got 28 compute nodes that each have 28 processors apiece, only 192 gigs of memory, terabyte of RAM. And then we also have the GPU compute nodes, which have the same setup as the compute nodes, but two of these have two K80s apiece, and then two of these each have one M40. So we have those as well. And then the storage is all the way at the bottom. Then we have our Samet cluster. So we actually named this after Jean Samet. She was one of the writers for the, I think, the Formac and the COBOL language. She was also the first female president of the Association for Computing Machinery, so we named our cluster after her. So this one has a head node. It only has 2 login nodes. This one, MicroWay, has really nice architecture diagrams of the pictures, really, of the nodes they sent us. So the top left is actually what a login node and a head node looks like. Then we've got the GPU nodes. So those are the ones that have these 4 nice little rectangles there. Each of these rectangles is a GPU. So we've got 10 of those, GPU 1 through 10. These all have 256 gigs of RAM. So people complained about the nodes on Senate not having enough RAM, so we bumped up the RAM there, terabyte of storage, and then each of these has 2 P100 16 gig GPUs. So you'll see that the picture there has four GPUs. We only have 2. GPUs are really expensive, and it's a little risky to kind of double down on a technology and buy. We saved a lot of money by buying less GPUs, and this has been good enough for now. One of the reasons we did this was it also gave us a lot of flexibility. So if I want to buy more GPUs now, I can put all the P100s on half the nodes, and then I can buy V100s and plug them in there. So that gives us a lot of flexibility to be a little bit more agile with the technology if something were to not work out. We also have a project-owned GPU node. So one of the things that came up was a certain project said, we want to use all these GPUs all the time, and we want to basically go out and buy our own DGX1 or something like that. And we'd rather them not do that, because then, if they use the resource for a year and the project gets canceled, it just sits in somebody's office and it doesn't get used. We'd really rather have everything managed by corporate. So what we did was we said to them, well, how much money do you have? And we found out how much money they had. We went to the vendors. We went back to MITRE and said, okay, what can we get with about this much money? They want all these GPUs. They want the V100s. And so we were able to buy them a new node. MITRE shipped it to us. I plugged it into the rack, hooked it all up. It didn't work perfectly, but eventually, after about a month, it was running. And now we have the scheduler set up so only users on that project can use the node. So they've got exclusive access to this node. They've got access to 4 V100 GPUs at all times. And they've got this nice new resource that they can use. They don't have to manage. They don't have to do anything. We handle all of it. It's got an FPGA-ready node. So we do a little bit of hardware development at MITRE. So we have this node where users can ship an FPGA to us. We plug it into the cluster. The scheduler allows them to have exclusive access to this, like the project-based node. And they can go ahead and use that. So we don't get too much use out of this, but people seem interested. But I really haven't had many people bite. So we kind of try to not put all our eggs in one basket with this one. So we've got the FPGA node if anybody does need it. So if you're not familiar with how a shared resource like this works, this is one of the hardest, I think, cultural things I had to deal with trying to get people to use a corporate HPC resource, is I would get all these, I'd take everyone through training, and people would show up to training, and they'd raise their hand, and they'd be like, well, when is it empty? When are people not using it? I want to, should I get on Saturday night and try to run all my code? And I'm like, no, that's not how it works. There's a scheduler. You just put it in the scheduler, and you just trust it, and you just let it happen, and it'll run. And then, they leave training, and they'll be like, okay, I'm going to log on Saturday. Okay, yeah, sure. So if you're not familiar with how this works, so you've got a login node, scheduler, and then here I've got like a little makeshift cluster. So it's got 4 compute nodes. Each of these compute nodes has 16 processors and 2 GPUs. So let's say I write my Moab submit script. I write my little script, which is how I submit jobs. We use Moab and Twerk on the cluster currently for our schedulers. So I'm going to say I want 1 node. On that node, I want 1 processor. And I don't need any GPUs. I'm just going to run my script called code.sh. Let's say code.sh just prints something out. So it's not parallel code. It's very simple. So I'm just going to run that. I put it into the scheduler. Scheduler turns it into a job, which I envision as rockets. It reserves the resource, and then it runs your code on there. And then all your files get copied back or written onto the NAS or however you have it set up. There's other types of jobs. So you can have things like job arrays. So if I'm running code that has let's say I want to run a model with a parameter sweep. So I want to run it on 10 different combinations of all these different variables. So I can put all my variable combinations I want to put into my model into a text file. And then I can set it up as a job array. So I've got, let's say here, I've got 6 different combinations I want to run. I can set a job array of size 1 through 6. Each of my jobs in my job array only needs to run on 1 node and 1 processor on that node. And I get all those launched. You can do accelerator programs. So if I want 1 node, 1 processor on that node, 1 GPU, I can reserve that as well. You can use OpenMP code. So if you're doing something that has inherent multi-threading, I think NumPy, TensorFlow, a lot of libraries have this already built in. You can set that up as well. And then you can also do if you've got parallel GPU code. So if you want to use 4 GPUs, you can have all those reserved as well, and it'll run perfectly fine. So walking through the user experience, what they do here is, so the first thing they do is attend training. So we do training every single week, Thursday mornings at 10 a.m. I did not do it this week because I'm here. But they do training, so everyone that wants to use the system has to go through training. And what we do in training is they get logged into the cluster, so I make sure that they know how to use PuTTY or a terminal, which a lot of our users don't necessarily come in knowing how to do, which makes it exciting. So they attend training. We get them to download PuTTY, log in, change their password, do all that stuff. We explain how a scheduler works, so we kind of talk them through those slides in a little bit more detail at times. And then we get them to submit jobs to the cluster. So we make sure before they leave that they can submit a job, run it properly, and get output back. So they attend training. Once they're done with training, they have full access to the cluster. So then they can start building their environment. So then they'll log in, they'll make sure that they have the right version of CUDA. They'll do something like Anaconda. Anaconda has actually made my job so much easier because you can just install Anaconda without root access. it's so much less work now. It's really great. We make sure they can do all that. If they've got Docker containers or something like that, we have Singularity on the cluster, so they can port Docker containers over. I'm also been working with Alex on his tool that he'll go into a little bit more detail on where they can build a container in Alex's area and then just ship it over to the cluster and run it there. They'll do debugging on their analysis and modeling code, so they'll make sure it works properly. We can run the cluster in interactive mode, so I can interactively reserve resources and go back and forth and set up something like a Jupyter notebook and test my CUDA code works properly. Then they do their scripts for job submission to the cluster, and then they submit their jobs to the cluster, and then step 6 is they get all the results back. So here's a really, really simple example that I'm going to walk you through kind of what it looks like to run GPU code on one of the clusters, on one of the nodes. So this example is taken from the documentation for PyCUDA, so I did not come up with this at all on my own. It just seemed like a really good example. It works perfect to copy and paste in here. So I've got import all my libraries. I'm going to do a multiplication. So I'm going to create a NumPy array A of just random numbers, B of random numbers. They're both of size 400. I'm going to multiply them. I'm going to store that result in something called dest. So for the destination, I'm going to multiply A times B, store it as dest, and then I'm going to subtract the result of A times B minus A times B. So what we should get here is just a bunch of zeros. So this is my basic Python script. And then what I can do is, so I've got this command up top, so I'm doing an msub-i. That's how I run interactive code. So I'm basically just going to, it'll SSH me to the node, and I can run interactively, and I've got those resources reserved. That way no one else can be run on the GPU that I have reserved. So I've got a -i, interactive, -q for short, which means I'm just a little bit redundant, but that's the way we have to do it. And then -l is how I specify my resource requirements, so I'm saying I want one node and one GPU on that node. So the Q sub is what feedback we kind of get from Moab. It says that they're waiting for the job to start. I can see here now I'm logged into GPU1, so I can run Python 3 pycuda / hello world pycuda, and I get my nice array of 400 zeros, which is exactly what I was looking for. So that is how I can kind of do the testing and debugging. I can do something in IPython and run all these libraries and have them going. I can do CUDA code, I can do MPI code, I can do all sorts of stuff like that. So this is on our on one of our nodes that are reserved specifically for interactive jobs. So then what I'm going to do is if I want to run this in production, I want to run a lot more jobs. I don't necessarily want to sit there and run things in interactive mode, so I'm going to write a script. So one of the things I really like about the job scheduler, modern job schedulers, especially Twerk and Moab, is that if you can write a shell script, you can write a script that will submit jobs to a high-performance computing cluster. It's very easy. So you'll notice this is just a shell script, but I've got all these msub commands. I don't know how the coloring is there. It's good? OK. So I've got a bin bash. That has to be the first line, because Moab says that has to be the first line. Then I can give it a name. So I'm going to name my code pycuda hello world. As far as I can tell, there's no reason to give your code a name besides it's nice. Specify resources. So I'm going to say I want one node. I want one processor per node, PPN as processor per node, one GPU, and I've got a wall time of 5 minutes. So specifying a wall time helps the scheduler kind of allocate resources a little bit more intelligently. You can lie about your wall time. If you lie and say too little wall time, your job will get canceled. If you say too much wall time, you get kind of your hand slapped in the scheduler a little bit when you run more jobs. It doesn't trust you, so it might not let you run as quickly again. I'm going to put all my output and error into one file, so anything that would print to standard out or standard error all gets sent to one file. I'm going to put it in a file called pycuda hello world.out, and I'm going to -e and -v is just basically taking all my environment variables I may have and just pushing them along as well. So I'm going to print out my NVIDIA SMI details. I'm going to run my Python code, put all my environment variables in one file, and I'm going to print out this nice little statement that says job submitted by CE Harvey me, ran on whatever host name it ran on. And so here's my output. So all I do is I type msub run pycuda.sh, and then I can, on my login node, and then I can cat my output file. I can see my NVIDIA SMI details, so it ran on one of these Tesla P100 GPUs, executed my Python code, and I've got the exact same output. So this code actually ran on one of the GPU compute nodes. We've got our output. We're verified that the GPU is reserved properly. No one else is supposed to be using my GPU, so it kind of cordons that off. I didn't have to send emails to people asking to reserve the cluster on a Saturday night. I could launch up 100 or 1,000 of these, send it off, and just have my results when I come back. So a little bit, just getting back to generally what we do at MITRE. So I have 115 projects running on these clusters. They do all sorts of different research projects. If you go to the MITRE website, you can see a little bit more about what we do. But in general, it's a lot of text, PDF document analysis, anything from we have an entire corpus of legal documents. So we'll do machine learning analytics on those, video image processing. We do construction site analysis, all sorts of things in that area. There's a lot of large-scale simulation, but we also do a lot of embarrassingly parallel problems where people have built a model. It'll run on one processor, but they want to run it across a million different parameter sweeps. So having the HPC cluster and the CPUs for that has also been really useful. And then as algorithms develop, we've had a lot of our users switch from using the CPU-only Senate cluster to we're running a little bit more on the GPUs. And we have a lot of machine and deep learning projects, so all sorts of things in that area. Our users, we have about 291 users right now, and these are all active projects and active users that have just come on over the past 2.5 years. So this area has really grown at MITRE. So our users are from, our biggest department is actually from human language technology. So we have a ton of linguists actually running code on the cluster. So a lot of people doing FAA, air traffic controller, voice data. We have all sorts of things like that running. A huge corpus of topics, data analytics, transportation, cognitive science, signal processing, a lot of biometrics too. So these are kind of who actually runs in the cluster. And then we've got a team of, I think it's now, there's 4 of us that work on this. Only one person is full-time. We do account creation. We do training for the systems and schedulers. So if somebody goes through training and they don't get it, we will meet with them again, and we'll just kind of keep working with you to make sure you do it. You make sure you're comfortable. I deal with a lot of people that have, linguistics or psychology degrees and things like that, and we're really able to get them up and running on the cluster, which has been really exciting. We do project consultation meetings, so if somebody emails me and they have a project description and what they're saying they want to do doesn't make any sense, we'll meet with them and they'll kind of talk them through, like, this is how you set up a job array. Your code is or is not a good fit for GPU computing. These are libraries other people are using. Software installs, management, upkeep, all sorts of things like that. We try to keep it running all the time. They're big computers. A lot of things break, so that ends up being a little bit of our work as well. And we do ticket assistance, project questions, scheduler problems, parallelization help, trying to teach people how to use MPI, things like that, GPU computing, and all sorts of different topics. And again, it's all free. So unless somebody really needs me to install something crazy, and it's going to take more than 8 or 9 hours of my time, we just help out. So we've got that flexibility to help out and come onto projects a little bit at a time when they need assistance. So thank you. I can take more questions on this. I can take any questions on this at the end. And now I'll have Alex come up and talk about the container solutions he's working on. Thank you.
Yeah, so that's all nice, but how do we get up and running there? So in that environment, you can't just install software. You have to have everything configured the way you want it to be. Let's build another environment where users can do whatever they want. So the prompt for this was deep learning, machine learning users need a simpler platform to tinker where they can just download code from the internet and run it. The existing platforms just weren't quite flexible enough. So we built this thing, horridly named Container Manager Toolset. Basically, we use Lixie to provide system containers to every user that wants one. A user can provision as many containers as they want. So we develop SSH infrastructure to manage and access those containers. So via SSH, the users can provision containers and actually access those containers. And we also develop a little tool to interactively manage GPU leases. So from inside your container at the shell, you can actually decide which GPUs are attached to your container. So what that looks like is a user would SSH to this connection broker on a single host and would be routed to their container. So Alex would be routed to Alex's container and Bob would be routed to Bob's container. What that looks like is you SSH to register at the host that you want to access, and then you type in your credentials and your SSH keys are registered. So you can register any number of SSH keys on each host if you so choose. So with this system, what we do is we use the username to decide where you're actually going to be connected to. So we have a couple internal shells. We have a register shell, we have a container shell, and we have an admin shell. So in this case, the register shell allows you to register your SSH keys. With the container shell, that allows you to provision containers and do miscellaneous user operations. And the admin shell allows you to take various administrative operations. What that looks like to the user is that they SSH to containers at host, create a container using any number of pre-configured images, and then SSH into that container name at that host name to gain access to it. So there's very little new things that the users have to know. If the user knows how to SSH and follow directions, we're pretty much good to go. So we've started up people with a basic understanding of SSH very rapidly and allowed them to access the resources much more quickly than we would in other environments. We also have this GPU manager thing. So inside the container, users, when they run NVIDIA SMI by default, there's no GPUs connected to the container. When they run GPU get one, a GPU is assigned to that container, and like that. So The other thing that we do is we automatically release GPUs when they're no longer being used. So we pull NVIDIA SMI for GPU usage, and as soon as the GPU has not been used for 5 minutes, the GPU is released back into the pool. We also have functionality to wait for GPUs to be available. So if you're running all your stuff on one server, we can kind of have like a little poor man's scheduler. So you can just run GPU wait colon, Python train or something like that, and the system will wait until that constraint is actually satisfied. We have an info command, so you can see other people and what they're doing, what GPUs they have. We have a little web dashboard that shows which nodes are being used by who. So if this was an actual web page, I could hover over this GPU and see this is leased by this user and this container, and it'll also tell you how long they've leased it for. So here's a bunch of operations. I'm going to go through a demo in a minute here to show you kind of what this does, but you can basically take a lot of the existing LXD operations and perform them via SSH, and that's really nice, so users don't have to really learn anything else. It's just as simple as them running help and running these commands that are specifically designed to be used by users. So the goal for this is really you prototype, tinker, and build containers in this environment. We can run Docker inside that, and that's all powered by LXD underneath. Once we built those containers, we can ship them to customers, run them in the public cloud, or run them on the HPC cluster. So we have nice instructions on how to build Docker containers, port them to Singularity, and all sorts of things like that. So you can find all that here. So it's container-manager.gitlab.io/docs. Code is on the way very soon. We just have a few little licensing legal issues that we have to finish up. So with that, I'm going to demonstrate what that would look like, right? So this can actually be done by anybody. This is on the public cloud right now. So if you go to SSH register at gtcdemo.agartner.com, you can actually register with whatever username you want. I'll say Gartner. It doesn't matter. And then the password for everybody right now is test. I basically just disabled authentication. So what that does is it registers and stores your SSH keys in the system. Once you've registered, then you go to containers, and then run a help. Then you can see all the different commands you want to run. I'm going to run images right away to see which images are available to me, and then I'm going to ls. Shoot, that's going to break things later. I got to go re-register because I messed up my name and my key got associated with a different user. Normally this wouldn't be a problem because I wouldn't authenticate with the wrong user, but here we are. And we're back. So I have my old containers that are part of the later demo, but what I could do is just create image test2, wrong image, test2. It's going to provision all of that out. And then when I log out and log back in as that container name, I'm going to be dropped transparently into that container. And that's really cool because we can use all the native SSH things to do whatever we want. So we can SSH port forward, X11 forward, SCP things just normally, and that works really well. So now I'm inside that container. No GPUs. Let's see, GPU info. Nobody's using any GPUs. I can GPU get one. And now I have a GPU attached to my container. So that works really well. And people seem to really like it. So let's look at some other things that we can do. I have some other containers already provisioned here. Let's talk about this first. We manage file system projects for users, so we provision local volumes, and we also manage NFS mounts directly as part of this interface. So I can say project ls, and I can see a number of projects that are available and configured on the server. So inside of each of these projects, if you see the tags being local, that means a local volume is being provisioned on the node. And if you see an NFS tag, that means that there's an NFS mount actually configured. So I can make containers, and I can make containers as the user and attach whatever projects I want to them, and I basically delegate the access to those projects to the users. So in the first versions of this, what we had to do is actually have an administrator attach those volumes to those containers, but now we have delegated that to a user. So long as I'm actually allowed to attach to the project, I can interactively create a container and attach that project to that container. So I just say a project attach, project shared test. It will create a local volume if it doesn't already exist, and it will attach all of the volumes. And so long as I'm allowed to access those projects, those will be mounted. So there's an admin interface where I can manage all of that. So I can just say admin@gtcdemo.agardner.com. Group ls. So we kind of have a little thing where we have groups, which are a combination of users, remotes, hosts, administrators, tags, a bunch of stuff all piled into one SQL table there. But basically, I can just say group update add user Gartner shared. And that will add that user to the group. And then from there on out, a user can attach whatever they want to so long as they have access to it. So you might have also noticed there's also a read-only tag. That means that if you're not an administrator of that project, you are mounted, you can only mount that project with read access only. We also have this very convoluted system of token management. So for some projects, we need to restrict access to the data only to hardware tokens. So that means that you need to have a YubiKey or something like that. Basically what happens is you can provision containers, you can take all these actions without a hardware token by default, but if you attach to a project with a hardware token required, it then requires you to use a hardware token for that container for the rest of the time. So basically it dirties that container, and then you have to use a hardware token in the future. So let's look at what a user might do on one of these containers. So I'm going to SOX 5 proxy into my dev container here. I have a bunch of stuff already running on it, so I'm going to tmux attach. I have code server running. So what code server does is allow you to run VS Code in a web browser. So all of these things that we're going to run are all running inside my container on a cloud server right now. We're entirely on premises for the most part, and that's kind of our use case for this tool set. So I can go over here to localhost 8443, and now I'm running VS Code inside my container. So I can load it up with all my plugins, do all my debugging, do all of my development, all inside this container environment. And what's really great about that is that means we don't have to buy workstations for each individual user. We can just give them a big cloud server. When they need to use the GPUs, they can just attach them as needed, and they fall back into the pool later on. Another thing we could do is we could run Docker containers inside our container. So I can just say sudo docker run, nginx or whatever app container we wanted, and it would be running inside that environment. Of course, you can't touch any of that until you SSH proxy inside there. So it's all secure by default. You can basically run whatever you want, and it's all controlled. Now I could just go to localhost 80, and we would show, welcome to nginx. This is really helpful for full stack developers, front-end developers who need to use GPUs, run a model or something while developing on their applications at the same time. So I can be editing, just my front-end code here, looking at it here, and then running a third container inside this environment to be doing inference and other tasks like that. Let's see. Yes, so another fun thing, I don't remember where I put that, is using a program called Xpera. So if you've ever tried to X11 forward over the network, like I VPN from San Diego to DC most of the times, doing X11 forwarding over connections like that is basically not possible. So what Xpera allows you to do is encode your remote X session and forward it over to your host, and then Xpera client decodes the session and allows you to interact with things very quickly. So I think I still have the server running here. So basically what that looks like is you run Xpera start on the container or any other SSH server that you have. It starts up the server, and then you run Xpera attach on your client. So if everything went according to plan here, I now have a native X11 application running remotely. And this is cool because it actually is fast and works really well. So I can attest to the fact that you can run this 3 levels of VPN deep and it still is really fast. So if you want to run a remote web browser on your container, you can totally do that. So I actually did pull up the Virt Manager thing for KVM, and you could technically run KVM VMs inside your container, kind of inside-ish, whatever. But let's say a couple of the things that I had seen before is people wanted to use native apps that were doing like LiDAR things and really, really intensive stuff. And this is a completely free solution to be able to do all of that kind of stuff remotely. So Xpera has a bunch of different features and is really cool, and you should definitely look into it more. Let's see. Yeah, so the whole reason this existed, right, is we kind of isolated this area, this getting started area that wasn't very well covered. So we didn't want to buy everyone a workstation. There's just not that much money, especially because we want to maximize GPU utilization and reduce costs. And the other great thing is I can do this work from anywhere. I can just be on a VDI, I can be on a laptop, I can be on my home computer, wherever it might be, and do all the work in one centralized location. And that really works well for employees that work in a lot of different locations. A lot of our employees, work remotely, work from a sponsor's location, might want to work from home, and this enables them to do their work wherever they are. So we want to continue to build out our pipeline to streamline, GPU access and the machine learning pipeline for our employees. And this was one part of it, was developing some infrastructure. And the suggestion that I would have for you is if you isolate these areas, don't just try and work around them. Build something that suits your use case. Right? This did take probably 500 hours to build out all of this stuff, but it's enabling a lot of people to do stuff really, really fast. Now users, instead of guessing whether or not their software will install correctly places, can simply provision out a new container, run through their scripts, and just see if it actually works. And that is really, really positive for rapid development of capabilities. Yes. The other thing, one other random thing that I've been working on recently is a GitLab CI plugin for all of this. So what that might mean is that GitLab CI can make a container inside this environment, deploy all your code. If it passes, if your build passes and all of that, the container just gets deleted. But if it fails, then the container just stays there, and then you can interactively debug it. So we have another feature that's been kind of developed for that called sharing. So by default, you can only, well, either the internet died or my connection died, or somebody tipped over the cloud instance. We have another tool called share, which allows you to do a lot of things like that. So let's say I want to share my container with other users, especially like let's say we have a production copy of our app running somewhere. We can make a container, share it with that project, and then all users who are part of that project can access that container. And that's really to build into the whole CI pipeline stuff. So maybe a CI user actually builds things, but then they share the container with all the other users. So when a container would be shared, you would have one name for everybody. And I don't have a good demonstration of that right now because I don't have multiple users, but it actually works very nicely because then users can do the same thing where they can SSH forward into the container, and it's pretty nice. So let's see. Right, so we have an internal system where people making cool stuff can do more cool stuff. So we're hoping that somebody in leadership thinks this is cool and continues to fund it. Like I mentioned, soon it should be all up on GitLab. I know I was able to provision out a system that did all of this with 1 or 2 scripts. We're aiming to automate it as much as possible. And by keeping everything in the container side of things, we allow hosts to be very upgradable and lightweight, and hopefully will be persistent and stay around for a long time. Cool. Did I miss anything? Yeah, that's all.